The final thing that we have to do is we have to find areas of regions bounded by polar curves. So rectangular functions are graphed on intervals from a to b that extend from left to right. We graph a function, and then we go from a to b, and when we find the area, we break this up from left to right into rectangles, and we get a Riemann sum. The x-coordinate here is the independent variable. Similarly, polar functions are graphed on intervals from theta 1 to theta 2 that extend counterclockwise. This is because theta is the independent variable. So when finding the area bounded by a polar curve, we will use integration and we will integrate over an interval to the counterclockwise direction. So here's the basic gist of it. If I pick an interval from theta 1 to theta 2, let's say here we have theta 1, here we have theta 2, and theta 2 could have been in the second quadrant or third quadrant. Again, this is really theta 1 and this is really theta 2, but we like to label the thetas outside here, just convention. So here's the game. I want to find the area of this region, which looks kind of like a wedge. So we do what we did before. We simply break this up into a whole bunch of skinny wedges. And you notice when we do this, each of these wedges has a point at the pole. They're all connected at the pole. So then we start labeling this. Well, okay, so this is theta 1, theta 2. So then we could call this, this was bad labeling. Let's call this theta start sub s and theta e for theta end. And so then this would be theta 0, this would be theta 1, theta 2, theta 3, and so on up to theta n. We're going to have n of these. And of course, just like before, dot, 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 and then we have theta sub k. So here's the basic gist of it, and I'm not going to get into the particulars. But if you remember from either geometry or the summer assignment, or you just happen to have a good memory, the area of a sector of a circle, this shape here, is 1/2 theta r squared. So all that we're doing now is we're going to find the area of each of these itty bitty teeny tiny wedges. And when we do that, since they're all wedges, the area of the kth wedge up here will be 1/2 delta theta, because in this case, this theta will be so tiny it will be a delta theta. It'll be theta 1 minus theta 2, or theta 2 minus theta 3, which I can just call delta theta, assuming they're all the same, times r squared. And then what we do is, as we did before, we let theta get smaller and smaller, delta theta get smaller and smaller and smaller, because the number of thetas, the number of these wedges is going to get bigger and bigger and bigger and bigger. So each of these get skinnier and skinnier. And then we sum them all up, and then we take the limit as n goes to infinity, yada yada. So finally, we wind up with the exact area being the integral from theta beginning to theta end, or theta start to theta end, of 1/2. The delta theta becomes a d theta. And the way this is written is we tend to pull this out, and we have r squared d theta. And that is the formula that we're going to wind up using, as you can see. Unfortunately, most textbooks, when they do this, call the starting point theta 1 and the ending point theta 2. That's what the convention will go by, but it just doesn't work when we're deriving it, because we like to use the subscripts to represent like the theta defining the first rectangle, the first arc, the second arc, and so on. Anyway, determine the area of the inner loop of the limicon. So here's the inner loop of the limicon. And I want to find this area. So again, it's important to note, as I mentioned, that when we find this area, we do it radially. Notice that this entire region, every point, if I draw a line from the pole to the point, the line doesn't cross over anything. This region is adjacent to the pole, and that's important. That's as important as when we do rectangular areas, realizing that the region we want the area of is adjacent to the x-axis. There's no subtracting going on here. We just take an integral of a function and we're done. Same thing here. We just take an integral of a function and we're done. The only problem is we need to figure out what the theta is. So again, here's where theta is 0. Here's where theta is pi over 2. Here's where theta first hits a pole. So r is 0 there. So I set my r equal to 0. r is 0. I solve, I get negative 1/2 equals cosine theta. So we get that theta is 2 pi over 3 and 4 pi over 3, which makes sense. The first time we go through this, the theta is 2 pi over 3. After we're done, the theta is 4 pi over 3. So this is simply a matter of finding the area. That's 1/2 the integral from 2 pi over 3 to 4 pi over 3 of 2 plus 4 cosine theta squared d theta. This is another integral that we could put in our calculators. Most of the polars are, and we get the answer. The other way to look at this, of course, is once again to use symmetry and realize that this region here can be separated into two equal pieces, from 2 pi over 3 to pi, and from pi to 4 pi over 3. So I could just find the area of one of those, 2 pi over 3 to pi, for example. And then when I get the answer, double it. Or I could do the same thing, only integrate from pi to 4 pi over 3. And all three of these integrals will yield the same exact solution. So if the region is adjacent to the pole, then this is a pretty straightforward problem. Just use the formula, figure out what your beginning theta is and your ending theta is. But it does get a little trickier. So here we have a cardioid. Looks like a cardioid. And a circle. I want to determine the area that lies inside. This is the cardioid. This is the circle. How do I know? Here the radius is constant. That makes the circle. So it has to be inside the cardioid and outside the circle. So that would be, if you look at this as like, for those of you that play video games, Toad, the Mushroom Kingdom's character. Or this could be some guy that just has a very, very bushy hairstyle. We are looking at the area that lies inside the cardioid and outside the circle. It's the region that I just traced over. And you'll notice there's an issue here. That region is not adjacent to the pole. So that's one thing that we're going to have to take care of here. The other thing we're going to have to take care of, we're going to have to figure out what we have to integrate from. So the very first thing we're going to do is we're going to look and we're going to say, okay, so where does this region start? Well, if I'm going counterclockwise, it starts here. And now I need to figure out my region is. The only way I can fill my region up with these radial lines is to either go to the circle, but that's not enough. I need to go out to, because the region is bounded by the outer curve. And you'll notice when I do this, the lines are being drawn inside of the region I want, but they're also being drawn inside the circle, the region I don't want. So what we're going to have to do is we're going to have to use a little geometry and some subtraction. So if this is theta 1 and this is theta 2, I'm going to have to integrate this entire thing, which would get me the region that is currently highlighted all in red, and then I'm going to have to subtract from it the part that I don't want. And the part that I don't want is the part that I am now outlining in blue. I don't want this inner part right here. So I'm going to have to do some subtraction. And there are a lot of ways that I can do this. So the first thing I can do, and we'll figure out what theta 1 and theta 2 are in a minute, is I can say, okay, let's integrate from theta 1 to theta 2 of the outer curve, which would be r squared, which is the cardioid. And then subtract from it the area from the inner curve, which would just be 2 squared d theta. So when I do that, the first one represents the area wherever there is a red radial line. And notice that that includes this here. If I draw a red radial line out, it includes this. And I want to exclude that. So after I deal with the full area, I have to subtract the inner area. And this is very similar to when we had to find the area between two curves. What we said was, okay, let's look at the area bounded below by the top curve, and then we'll subtract from it the area bounded by the curve the lower curve, and we just get the area in between. This is similar. And the reason we have to do this is because my region does not adjacent to the pole. In the same way, this region that I'm looking is not adjacent to the x-axis. So rectangular coordinates are relative to the x-axis, polar coordinates are relative to the pole. Another way to do this is to realize that this is a circle and just try and figure out what percentage of the circle this is, and then take its area using pi r squared divided by the percentage. So the last part that we have to deal with here is we have to deal with the points of intersection. So to figure out where they intersect, we simply ask, well, where are the r's equal? Just like we would for rectangular coordinates. So 2 equals 3 plus 2 sine theta. We get negative 1/2 equals sine theta. Sine is negative in the third and fourth quadrants. So, since sine is negative in the third or fourth quadrants, that means sine of and sine of pi over 6 is 1/2. So this would have a reference angle of pi over 6. This would be 7 pi over 6. And this would be 11 pi over 6. So, following that this is from either the circle or the cardioid, and we are going counterclockwise, the theta in the third quadrant would be my 7 pi over 6, and the theta in my fourth quadrant would be 11 pi over 6. And I'm hoping at this point you notice that we have a problem. Because here I tried to integrate from theta 1 to theta 2. But theta 1 is larger than theta 2. If I tried to integrate this way, it would be going backwards. And I cannot do that. I'd wind up with negative areas, and it does not make sense. So really, in this case, I have to integrate. Well, I still have to integrate from this point around here. I can't integrate from 7 pi over 6 to 11 pi over 6. If I do that, I'd be looking at the region here and the region here. And that's a problem. This has to come first. The problem is the 11 pi over 6 doesn't let it, because 11 pi over 6 is bigger than 7 pi over 6. So what do? Well, 11 pi over 6 is not the only name for the theta at this point. Remember, we can deal with coterminal angles. So we can add 2 pi to this. And if I add 2 pi to this, or subtract 2 pi from this rather, if I subtract 2 pi from this, this is now negative pi over 6. I can now integrate from negative pi over 6 to 7 pi over 6. And that's one way to handle it. Negative pi over 6 to 7 pi over 6. The other way to handle it is if I want to start here and I'm calling this 11 pi over 6, this is then 2 pi. If I go around, this will be 7 pi over 6 plus 2 pi. So I could also integrate from 11 pi over 6 to 2 pi plus 7 pi over 6, which is 19 pi over 6. So either of these limits of integration will give me the same thing. This is what the area turns out to be once I actually integrate it. The other interesting thing to note is that if I go from negative pi over 6 to 7 pi over 6, that is a total radial distance, 7 pi over 6 minus negative pi over 6, of 8 pi over 6, or 4 pi over 3. So how does that help me with anything? Well, the total number of radians in a circle is 2 pi. So 4 pi over 3 is a percentage of this circle. In fact, it is 2/3 of this circle. 4 pi over 3 is 2/3 of 2 pi. So this area that I wish to subtract is simply 2/3 of a circle of radius 2. So the other thing that I can do here, instead of subtracting this, is I could also subtract 2/3 of the area of the circle, pi r squared, and this winds up being negative 8 pi over 3. This value here will wind up being negative 8 pi over 3. And in fact, we can see that because this is just a constant, 4. And when I pull that out, this is just minus 2. I'd be integrating d theta. I would get theta from negative pi over 6 to 7 pi over 6. And when I subtract those, this becomes 8 pi over 6 times negative 2 becomes negative 8 pi over 3. So I can do that with an integral, or I can do that with geometry. Unfortunately, this first part has to be done in the calculator. There's no way around it. Does it get any more difficult? No, it just gets different. Determine the area of the region outside the cardioid and inside the circle. Well, outside the cardioid and inside the circle is this region down here. Note that these are the same points of intersection that I already have, namely 7 pi over 6 and 11 pi over 6. And in this case, when I integrate, I am going counterclockwise. I'm not passing the point where theta is 0, so I can simply go around like I normally would. Note also that this region is not adjacent to the pole. So when I find this region's area, I will start here, and then when I go radially out to the further curve, I wind up including too much. I don't want to include, again, the blue area. Here is the blue area. So once again, this becomes a subtraction problem. This time, though, the outer function, 7 pi over 6 to 11 pi over 6, 1/2, the outer function, the outer radius, winds up being the circle. And then I'm subtracting the inner function, which is the cardioid. And this would be the area of that region. And again, if I wanted to, I could figure out that this is actually 1/3 of the entire circle. And I know that because in the previous problem, this was 2/3 of the entire circle. So another way to do this is to say, well, what's 1/3 of the entire circle's area that has a radius of 4? So that would be the same thing as 1/3 of pi r squared, which is 4 pi over 3. This should give us 4 pi over 3, just this part. I still have to do the integration of the second part because there are no nice formulas for the areas of cardioids. So the final part is the most interesting. Determine the area that is inside both of them. So in this case, there's not going to be any overlap. The area inside both of them is, if I'm going counterclockwise, this region that is adjacent to the pole. So I shouldn't have to do any subtraction. But you might notice something. Right now, all of my radial lines are being drawn to the circle. And then, once I get to 7 pi over 6, the radial lines are now drawn to the cardioid. So here, we have to break up the integral into two parts. And again, since I'm integrating here from 11 pi over 6 around, I might want to call this also negative pi over 6. And there are a lot of ways I could do this. I could go from 11 pi over 6 to 2 pi. Then I could go from 0 to 7 pi over 6, all while integrating the circle. And then I could go from 7 pi over 6 to 11 pi over 6 with the cardioid. So one way to do this is to go, okay, this is theta is 11 pi over 6. I'm integrating counterclockwise. This is where theta is 2 pi for the circle. So I will integrate from 11 pi over 6 to 2 pi of the radius squared, r squared. And then I will add to it, since now I'm also considering this as 0, the integral from 0 to 7 pi over 6 of the radius. And then deal with the blue part. That is not a good pen. The part inside the cardioid. This goes from 7 pi over 6 to 11 pi over 6 of 3 plus 2 sine theta squared d theta. And that will give me the area. Or I can simply do the circle in one shot and consider this for the circle as negative pi over 6 and say this is 1/2 the integral from negative pi over 6, integrate around to 7 pi over 6 of the radius squared plus, and then take care of the section in the cardioid, which would be from 7 pi over 6 to 11 pi over 6 of 3 plus 2 sine theta squared d theta. And both of these expressions will give me the area of the region that I'm looking for. So again, the interesting thing about these problems is, one, dealing with what happens when we integrate counterclockwise, but we cross over the positive x-axis. Because there, my theta is then going to be either greater than 2 pi, and I'll have to deal with it here, or my theta will start less than 0, and I'll have to convert my theta here. Because when we find thetas, we almost always find them on the interval from 0 to 2 pi. But that's not necessarily going to work, because if I integrate from 7 pi over 6 to 11 pi over 6, I would be dealing with this region that we did in part B. And if I want the region from 11 pi over 6 to 7 pi over 6, I have to convert either the 11 pi over 6 or the 7 pi over 6. Either way. The other parts to realize are, what is the outer curve? When I'm doing my region, draw these radial lines from the pole to the outer curve that's bounding the region. What is that outer curve? If I'm not intersecting an inner curve, then it's just the integral from theta 1 to theta 2 of that. If I am intersecting an inner curve, then I have to do some subtracting, as we had to do in the previous two parts. And then on top of that, what is this actual outer curve? Does it change? If the outer curve changes, then I also have to deal with it as two separate integrals. And that would be similar to what happened when we had two curves and I wanted the area bounded between them, and the top curve and the bottom curve changed places. I needed two separate integrals to represent the area. And that is everything as far as the area bounded by polar curves. And once again, this gets my seal of approval.